All right, so in this video, I am combining the two sections in Chapter 8 that we're going to do because Chapter 8.1 is not going to have a lot in it, and neither does 8.2. So it's just this one side of the page, and so we're just going to get through both of them together. So the first part in 8.1, we're going to talk about the sampling distributions. Well, the distribution of the sample means that it's the distribution that results when we find the means of all possible samples of a given size. And the sampling error is the error that's introduced because a random sample is used to estimate a population parameter. It does not include other sources of error, such as biased or sampling, or bias sampling, bad survey questions, or recording mistakes. It's just an error that happens. Now there's some notation in here that you need to be aware of. For the sample versus the population, the sample size will be a lowercase n, but the size of the population is a capital N. X bar is our sample mean, and the mu is the population mean. And if you see that, you don't know what it is, it's on your handout, it's mu. And S is our sample standard deviation, but sigma is our population standard deviation. All right, there are some characteristics of the distribution of the sample means. For any distribution of sample means, the larger the sample size, the more closely the distribution of the sample mean approximate a normal distribution. And the mean of the distribution of the sample means it equals the population mean. So the standard deviation of the distribution of a sample means is given by this expression of sigma divided by the square root of n. So we're just kind of talking about some of the differences in this between what happens in a sample and what happens in a population. Like, what do you use for the sample versus the population, and some of the issues that might come into play when we take our sample and apply it to a population, like the error. Now, for 8.2, we are going to talk about estimating the population means, which is using a sample mean to estimate the population mean. So suppose that we have computed the sample mean, which is X bar, for a single sample drawn from a large population. To estimate the population mean, which is mu, we're going to use the sample mean as our best estimate of the population mean. So we really don't have another choice other than to use the best estimate, since we only have a single sample mean. We'll compute a margin of error and use it to construct a confidence interval around our estimate. Based on the sample size, the sample standard deviation, we can then make a statement that gives us some idea of how good our estimate will be, or how much it is. A confidence interval is a range of values likely to contain the true value of our population mean. So we're going to work with a 95% confidence level in the material that we're using, but you could have other levels such as 90 or 99. But we're going to use a 95% confidence interval. So we'll find our confidence interval for our population mean by adding and subtracting the margin of error from the sample mean. So that means that we'll have X bar minus the margin of error to X bar plus the margin of error. We can write the confidence interval formally as X bar minus the margin of error is less than mu, which is less than the X bar plus the error. And we're going to use a 95% confidence interval, and the E will be equal to 1.96 S divided by the square root of n. We can use a sample mean as an estimate of the population mean, and the margin of error for 95% confidence interval will be looking like this. The margin of error, which is equal to that E, is what I just mentioned of 1.96 times S. S is our sample standard deviation divided by n, or the square root of n. So the confidence interval for a population mean always has the sample mean at the center and extends in equal distance from that when we add and subtract our margin of error. So to choose our sample size, in order to estimate the population mean with a specified margin of error of at most E, the size of the sample should be at least that 1.96 times the population standard mean, the sigma, divided by the error and squaring that. So basically what we did is we took this formula of E equal to 1.96s divided by the square root of n, and we moved things around and solved for the n. So if we multiply by n, the square root of n on both sides, and then divide by E, and then to find n, we squared both sides, this is what we end up with. And the sigma is the population standard deviation, and it's often estimated by the sample standard deviation. All right, so we've talked about some things. Let's go actually apply it. So we're going to look at the protein intake for men. So if we consider the daily protein intake data for a sample of n equals 267 men, with a sample mean of x bar equal to 77.0 grams, and a sample standard deviation of s equals 58.6 grams, we're going to find the margin of error for a 95% confidence level and construct the and then construct the interval of that. And how does this interval compare to the recommended daily protein intake for men of 55 to 60 grams? All right, so this is 8.2, example 1. So we need to take what we have and apply it in there. So we're looking at our formula of E is equal to 1.96s divided by the square root of n. So we're going to go plug in our numbers. So our S value, well, we find our n first, right? N is equal to 267. And then the S is 58.6. All right, so we'll have 1.96 times 58.6 divided by the square root of 267. Now you can just put this in your calculator, multiplying the top and then dividing by the square root of 267, and we will get 7.0 grams. So that's our margin of error. Now, to construct our 95% confidence interval, we're going to add and subtract the margin of error from the sample mean. So our x bar was equal to 77.0 grams. So we're going to add and subtract that number. So 77 minus 7 will get us 70 grams. And 77 plus 7 will get us 84 grams. So our confidence interval will be 70, and we're going to go ahead and put the decimal place just because of the preciseness so they understand it was 0.0 grams. So 70.0 grams is less than our mu, which is less than 84.0 grams. So this is saying that our population mean is somewhere between 70.0 grams and 84.0 grams with a 95% confidence. Now, it asked us a question, and the question was, How did this interval compare to the recommended daily protein intake for men of 55 to 60 grams? Well, 55 to 60, this is significantly higher, right? It suggests that that American men are consuming a different amount of protein than the recommended daily allowance. So it suggests that American men are consuming a different amount of protein than the recommended daily allowance of that 55 to 60 grams. All right. Okay, so let's go look at example 2. So for example 2, approximate the margin of error and 95% confidence intervals. So we're given some values here. So example 2, we're giving for part A, n is equal to 100, x bar is equal to 55 centimeters, and s is equal to 5 centimeters. And I want to find the margin of error and the confidence interval. Well, to find the error will be 1.96s divided by that square root of n. So 1.96, our s is 5, over the square root of 100. We can simplify this down a little bit. The square root of 100 is a perfect square, so we could multiply the top and over the square root of 100, which is 10, or you can just put it all in the calculator. I'm okay with that as well. So 0.98 would be our error. If we wanted to round that to 1 decimal place, that's what we did our last one at. If we want to round it to 1 decimal place, the 8 will cause the 9 to round, and this will become 1.0 centimeters. It'll make our math a little bit easier than if we're adding and subtracting 0.98. All right, so to find our confidence interval, so this is the error, we're going to have our mean, which is 55, minus 1, and 55 plus 1. So we're going to say that 54 centimeters less than our mu, less than, 56. I wrote 54 twice. Sorry about that. 56 centimeters. So this will be our confidence interval. That somewhere between 54 centimeters and 56 centimeters, we would expect to find our population mean. All right, and let's go look at part B. Part B is the same process. We are given that n is equal to 36, x bar is equal to 60.9 seconds, and s is equal to 4.3 seconds. So we're going to do the same math process as the previous problem. So we'll have E is equal to 1.96s divided by the square root of n. So 1.96 times 4.3 divided by the square root of 36. Now again, we can either go straight to the calculator, or if you notice that you can take the square root of 6, you could simplify first. 8.428 divided by 6, because the square root of 36 is 6, will get us 1.4 seconds. Now in this case, we're going to keep that decimal. We're not going to round any further than that. And so we're going to take our 60.9 seconds and subtract 1.4, which will get us 59.5. And we'll take 60.9 and add 1.4, which will get us 62.3. So somewhere between 59.5 seconds and our 62.3 seconds will be our population mean, and that's with a 95% confidence interval.